first order and first degree. We have discussed exact method, then how to, if it is directly not exact, how to make it exact by finding integrating factors, all these things. Now we discuss ordinary differential equations of first order and higher degree. Previously all the first order and first degree. Now we discuss first order and higher degree. Particularly we will discuss three cases in this category. First case is case 1, solvable for p. By p we will denote this derivative of y with respect to x. So that first order derivative dy dx, we will denote it by p. This equation will be of this form: f of xy p equal to 0. That means f is a function of xy, dependent variable, independent variable, and the derivative itself. So a function of this form, based on its category, we can solve it. So first case we see, which is solvable for p. Solvable for p means if we can express p in terms of other variables, that is x and y. Means if we can separate p from x and y, it belongs to this category, case 1, solvable for p. See this example, this equation x square equal to 1 plus p square. P means dy dx here. In case of when we discuss partial differential equation, p has another meaning. It is del y del x or del z del x, etc. But in ordinary differential equation, if p is given, p means this dy dx. So this obviously we can solve for p. That is, we can separate p from other variables. So we can write p equal to plus minus of this, and since p is dy dx, so this equation becomes dy equal to this expression into dx. Now integrating both sides, in the left hand side we have y, and in the right hand side this has a direct formula, well-known formula, which is this we have written and got the solution. Solvable for p is an easy case. Just you need to separate p from other variables, then you write the integration differential equation by separating the variables, then integrate them. This was much simple. Next, see this example: dy dx minus dx dy into x by y minus y by x. This we can write dy dx equal to p. So dx dy is 1 by p. 1 by p equal to this. Now if we simplify, this is not as simple as previous one. Directly we cannot separate p from others. So we put it into quadratic form. Simplification, we get this form. And then in the next step, if we factorize it like this, then we have one factor as p minus x by y, and other factor is p plus y by x equal to 0. Now we can solve for p. Either this will be 0 or this will be 0, or both will be 0. Therefore, that first factor equal to 0 gives us this equation, which we can solve directly by putting it into exact form, b of xy equal to 0. So our solution is xy equal to c1, an arbitrary constant. Again, if this expression is 0, p minus x by y equal to 0, then we have this equation dy dx equal to x by y, which we can solve directly by integrating. So we get x square minus y square equal to another arbitrary constant C2. We'll have x square by 2, y square by 2. After that, we multiply both sides by the constant and adjust with another constant, so we call it C2. So now either this is a solution or this is a solution. Therefore, you can write finally the combined solution or general solution is product of these two. This multiplied by this equal to an arbitrary constant C. Okay, so that is the method for solving for P. Very simple technique. So remember, it is applicable for first order and higher degree equation. Higher degree means what is the degree of this equation, x square plus 1 plus b square. Order is 1 because only dy dx is there, and the highest power of the first order derivative, that is 2. So degree is 2. Is first order higher degree. This one also, initially it looks like power 1, but not actually, because it is p minus 1 by p. So when you get rid of the radical, this is in fractional form. When you get rid of the radicals or the fractions, then whatever is the highest degree of the derivative, that is the degree of the differential equation. So after getting rid of the fractional form, we have highest degree as 2. That's why it is also first order and higher degree, second degree equation. So first case was solvable for P. Next case is solvable for Y. Solvable for Y, the working rule is put the given equation in the form y equal to function of x and p. That means if we can separate y from other variables, that is x and the derivative dy dx, then it belongs to this category, solvable for y. So first you separate the variable y from other variables. Next you differentiate both sides with respect to x. Third step is eliminate p from the given equation and the equation obtained. Given equation is this, and equation obtained means after differentiation, whatever you get, that one. So from these two, you eliminate p. And the last step is the p eliminant is the solution. When you get rid of p, whatever remains, that is the solution. Let us see an example. Solve this equation, p square plus y equal to x minus 3 into p. So here you see it is, if you can make it solvable for p, then also it may be possible. Then maybe like earlier, you have to factorize and find the roots of p. But solving it by that case, solvable for y is much easier, because y, only one y is here. So y we can very easily separate from other variables. So we can write y equal to x minus 3p minus p square. So it belongs to this category. Solvable for y. Next step is differentiate both sides with respect to x. So here you have dy dx. Here you have first p into, because there are product of two variables, so p into derivative of this, which is 1 plus x minus 3 into derivative of this dp dx minus derivative of this 2p into dp dx. So in the left hand side we are writing p and this same thing, so pp here gets cancelled. What remains is x minus 3 dp dx minus 2p dp dx equal to 0. Now you take dp dx common, so you have x minus 3 minus 2p equal to 0. So now you have two cases, either dp dx equal to 0 or this factor is 0. If dp dx equal to 0, then you have directly, by direct integration, you get p equal to c. And if this is 0, you solve directly that P equal to x minus 3 by 2. So these two solutions for P we have obtained. Now last step is eliminate P using this equation and the given equation. So how to eliminate P? You just need to replace the value of P in the original equation. So 1 and 2 gives us a solution y equal to x minus 3 into c minus c square. Just we have replaced the value of p by c in the given equation. Okay, so this gives us one solution. Another solution may be obtained by eliminating p from 1 and 3. So if we use 1 and 3, the solution is, that is, just replace the value of p in the given equation, you will have this expression y equal to this, which is x minus 3 whole square by 4. But here one thing to notice is that there is no arbitrary constant in this solution. Although this is a solution, but there is no arbitrary constant. But here you have one arbitrary constant. This is a first order differential equation. So in first order differential equation, in the solution, you should have one arbitrary constant. Now, do you understand the presence of significance of the presence of arbitrary constant in the solution of a differential equation? For example, if the differential equation is dy dx equal to m. Suppose a differential equation is there, dy dx equal to m, where m is a constant. Then what does it represent? Can you tell? Geometrically, what does this differential equation represent geometrically? Dy dx equal to m.
It's a straight line with zero slope.
Straight line with
a constant slope. Straight line.
Constant slope. So how many straight lines?
One.
That's correct. It represents a straight line, but not only one. So how do you do it? If you solve this differential equation, what do you get? Dy dx equal to m. Dy dx equal to m. If you solve it, what is the solution?
y बराबर mx plus c.
Y equal to mx plus c. So that y equal to mx plus c represents what? Do you remember?
Straight line.
Straight line, sir, with zero slope.
Not
Yeah, one,
zero,
one.
not
One,
zero
sorry, one, sir. One.
So it's not 1. Y equal to mx plus c. What is that m?
M is slope, so dy by dx.
Yeah, m is the slope. And
Yes, sir.
c means?
Intercept.
Yeah, intercept from the y-axis by that straight line. Okay. So it represents the straight line with slope m which intercepts that c from y-axis. So where c is the arbitrary constant, means you can change the value of c. C can be any constant. So from that you try to understand what does it represents. It represents a family of straight lines with slope m. All the straight lines which have slope m and different intercepts from y-axis. Understand? That is the significance of presence of arbitrary constant. The solution of differential equation gives you a family of straight lines in this case. Not only one, it's all the straight lines with slope m, constant slope m, but different intercepts. Okay, so there is the thing. It gives you all these straight lines. So just one equation, but it represents too many things. A group of things it can represent. Like in your group, CSE, this mathematics group, all the students who are having this common paper are included. So one group represents all of you. So like that, one differential equation represents all such straight lines satisfying this particular property. So this is the significance of the presence of arbitrary constant. When you vary the arbitrary constant, you get a different element of this group. So that's why in the solution of a differential equation, the existence of arbitrary constant has to be there. So here, although this is a solution, you can see by putting here, by replacing y equal to x minus 3 square by 4, that it will satisfy the equation. So it is a solution, but there is no arbitrary constant. That means it is just a particular solution, one solution. We are not interested in only one solution, but a family of solution. So that's why we will take this as the general solution, because this solution has the arbitrary constant. This one does not have arbitrary constant. That means it is just one solution. You can write this also, but arbitrary constant, but the main solution or the general solution is this one, y equal to x minus 3c minus c square. Okay. So that is the case solvable for y. Same as earlier, you write y as a function of other variables, then differentiate both sides with respect to y, and then you eliminate p from the equation obtained from this step, and using the original equation, that p eliminant will give you the solution. Then we have another case which is solvable for x. Exactly similar procedure. Here you have to separate x from other variables. Then differentiate both sides with respect to y. The reverse of previous procedure. Previously we were differentiating with respect to x. Now obviously we need to differentiate with respect to y. Then you solve for p and eliminate p by putting its value in the given equation. The p eliminant is the solution. See this example, y equal to 2px plus yp square. So it depends on you which method you want to apply. Three cases we are discussing till now. The first one was solvable for p. So if you can do that, no problem. But solvable for p may be slightly more difficult than other ones. Then you had solvable for y. So solvable for y is also possible if you separate y from other variables. But solvable for x is easiest here because only one x is present in this equation. So we write twice x equal to the other variables on the other side. Then differentiating both sides with respect to y, we get this. Then after simplification, we arrive at this equation. 1 by p plus p equal to this. Now we simplify further and obtain this equation. So calculation is up to you how you simplify it. That you will check at home. Maybe there are some easier steps. So from here, this expression gets cancelled. 1 plus p square by p, 1 plus p square by p. This one gets cancelled. So what remains is this 1 equal to minus y by p into dp dx. So this equation is very easily solvable by separating the variables. Here you have dp by p and dy by y equal to 0. So if we integrate, we have log p plus log y equal to log c. So the expression for p is c by y, where c is the arbitrary constant. Our next step is to eliminate p from the original equation and the equation obtained in this step. So we have obtained only one equation here, e equal to c by y. Just put its value in the original equation, e equal to c by y. By putting it, we have y square equal to c into twice x plus c, which contains one arbitrary constant. So this is the solution. So these techniques are quite simple, first order and higher degree. P cases, one is solvable for P, then solvable for Y, and solvable for X. Here you have some more problems on this category, solvable for P, another problem on solvable for P, solvable for Y. So some problems are there, you try to solve them at home. Next, there is another equation, Lerod's equation is this. So these are equations of the form y equal to px plus px plus function of p, f of p. So these are equations of this form y equal to px plus f of p. The procedure is that differentiate this equation with respect to x. So you have dy dx plus p into derivative of x, which is 1, plus x into derivative of p dp dx plus f dash p into dp dx. When we differentiate this with respect to x, we get by chain rule f dash p into dp dx. This implies x dp dx plus f dash p dp dx equal to 0, because this is p and here you have p, they get cancelled. We have this expression. Now if you take dp dx common, then we are having x plus f dash p into dp dx equal to 0. From that we are writing dp dx equal to 0. And so by integrating this dp dx equal to 0, we have p equal to c. Now, there was another factor x plus f dash p also. This multiplied by this equal to 0, we have considered only one case, dp dx equal to 0. What about this one? Can anyone tell?
So there will be no arbitrary constant. That's
There is no arbitrary constant.
when we put it and integrate it, it's not a
you may have an arbitrary constant, because you see it is f dash p. F dash p means df dx, derivative of f with respect to x. So if you integrate it, an arbitrary constant will come. Question I am asking that this, when x into y equal to 0, what happens? Either x equal to 0 or y equal to 0, or both are 0. And these cases are there. Here we have considered only one case, that dx equal to 0. What about this? This also can be 0. Why we did not consider it? Did not consider it because it cannot be 0. So can you tell why it cannot be 0? X plus f dash p, this expression cannot be equal to 0. What is the reason? Anyone think? Because this expression to be 0, what should you have? F dash p equal to should be equal to what? So that this expression becomes 0. F dash p should be equal to
0 and
Minus
x.
x.
minus x. If
Minus
f dash p equal to minus x, then only this expression becomes 0. But can it become minus x? F dash p means, f of p means a function of dy dx. P means dy dx, so a function of dy dx. And f dash p means derivative of that dy dx. So this is a function of p, dy dx. So dy dx must be present here in this expression. If dy dx is present here, it obviously cannot be equal to the single variable x or minus x. That's why this f dash p cannot assume the value minus x. That's why this factor cannot be 0. Understood? That's why we have considered only this factor. Only possibility is that this factor is 0 if dx equal to 0. That is the reason we did not consider it, because f dash p means it is a function of dy dx. A function of dy dx means dy dx must be present there. If dy dx is present there, it cannot be equal to a single variable minus x. That's why this cannot be 0. Anyway, after solving this, we have got this p equal to an arbitrary constant. Next, we replace this value in the given equation. So we obtain y equal to cx plus f of c. That is our solution. So it is simple. If you can determine that the given equation is Clairaut's equation, directly we can write the solution as y equal to cx plus f of c. Means you just need to replace the value of p by an arbitrary constant c. The procedure is explained in these steps why this becomes the solution. So for example, if we want to solve this, p equal to log of px minus y, let us see if we can put it into this form. Originally it is not in this form, so this means e to the power p equal to px minus y. So we can separate y from other variables, y equal to this. So it is now in this form, y equal to px plus a function of p. The function of p is e to the power p here. So therefore it is in Clairaut's equation form. Therefore its solution is directly you just replace the e by c, arbitrary constant. Therefore the solution is y equal to cx minus e to the power c. Directly you can write, or you can show these steps also. No problem. If you want to show, you can show, or direct, or otherwise you can directly write, because it's an established method. If we have discussed here how if you replace p by c, then we have a solution. This is the solution. Next, we have another example, y minus px into p minus 1 equal to p. Let us put it in Clairaut's equation form. Y minus px equal to this, p y equal to px plus this. Clairaut's equation means y equal to px plus f of p. Our f of p is this. So it is in that form, Clairaut's form. So therefore, general solution is just p replaced by c, nothing else. So simple. Another example you see, dy dx whole square minus this and this. So here, so directly always you will not understand which this is in which form, then you can see one by one. So obviously it is not first degree, first order, but not first degree because of the presence of higher power of p. So these are second degree equations. One by one you will check first whether we can solve for p, or solve for x, or solve for y, or it is in Clairaut's form. So in your syllabus there are these 4 cases: solvable for p, solvable for y, solvable for x, and Clairaut's form. Yes, it must belong to one of these 4 categories. So here we try to put it in Clairaut's form. After simplification, we make left hand side a perfect square, y minus px whole square equal to this, so y equal to this. Now it is in Clairaut's equation form, y equal to px plus f of p. Therefore, general solution is y equal to p replaced by c, cx plus s square, c square plus b square. Another equation here, sin px cos y equal to cos px sin y plus p. If we change sides, then we have sin a cos b minus cos a sin b, which is sin a minus b. On the left hand side, we have sin px minus y equal to p. If we apply inverse function, we are having px minus y equal to sine inverse p, y equal to px plus sine inverse p, which is of the form y equal to px plus f of p. F of p is this sine inverse p. So it's in their equation form. Therefore, the solution is, next you don't have to do anything, just increase p by c, and you obtain the solution. Okay, so that's it. This completes your that unit, fourth unit. This time the syllabus seems to be much easier than previous semester. Already one unit completed, so it contains only these topics. You from that book you practice more problems on these topics, and I'll provide you the problem set also. Any question? I hope not, if you have understood. So that will be all for today. Next class we will start another unit. Let me take the attendance. Abhijit, Aditya, Anjali, Ankur, Kush, Baharul, Vikiran, Rosmandan, Devanshi, Deepjyoti,